Okay, guys, so we are going to do a little bit more practice on the math stuff when it comes to these light calculation type problems and examining our electromagnetic spectrum a little bit better. So for this activity, we're going to need our calculator, so make sure you have your calculator nearby. And we're going to need your notes handout that we just took, especially the electromagnetic spectrum thing that we just mapped out, because we're going to actually be able to try to figure out how to compare the different stuff from the electromagnetic spectrum in terms of wavelength and frequency and energy. So eventually you'll need to have this memorized, which once again, if you just remember red Martians invade Venus using X-ray guns, and if you know the relationships between energy, wavelength, and frequency, and honestly, if you can kind of just visualize how the wave starts to look, it should hopefully be able to make things a little bit easier as you navigate through these questions. So in fact, the first page, you don't even need your calculator for. You just have to, have an understanding of the electromagnetic spectrum. Okay, so let's get started because I'm super excited. Okay, it says in the diagram below, which wave out of these two waves has the higher frequency? Now, frequency is a measure of how many wave cycles happen per second. Well, frequency and wavelength kind of go hand in hand. Like the higher frequency wave is going to have a shorter wavelength, right? And a lower frequency wave is going to have a longer wavelength. So what I kind of like to do is I'm like, okay, visually to check myself, I can kind of, mark the wavelengths of each one of these waves. For this guy, that's his wavelength. And for this guy over here, his wavelength, it's a little bit shorter. Well, we know wavelength and frequency have an inverse relationship. If one is a high value, the other one must be a low value. If one is a low value, the other one must be a high value. Because remember, in our calculation equation, when I multiply both of those things together, you always have to equal the speed of light, that constant of 3 times 10 to the 8th meters per second. So what that means is the one that has the higher frequency, remember a higher frequency, I'm thinking like that. Oh, higher frequency means a shorter wavelength, okay? So when they say explain, you guys, I'd be totally fine if you say a shorter wavelength. Therefore, that little triple dot symbol in science means therefore, which you know how much I do not like words. That is an amazing way for you to explain things to me. So a shorter wavelength, therefore a higher frequency. So here I've answered, I have not answered the question. They're asking which one of these has a higher frequencies. So how about we give that higher frequency wave a circle? And then there's our explanation coming in hot here. Okay, question number 2. It says in the diagrams below, which wave has the shorter wavelength? Well, I'm pretty sure these two waves are exactly the same two waves that I just looked at in the previous problem, but just to make sure, let's mark off those wavelengths. The one that has the shorter wavelength is this one. It was also the one that we said had the higher frequency, right? Shorter wavelength, higher frequency, that's the inverse relationship between those two properties. But on the explain thing, we could say the wavelength, which is crest to crest, is shorter on the wave to the right. And honestly, you drawing that on a wave, that is a great explanation. This shows me that you are wanting my attention to be drawn to. You have mapped out those wavelengths, and hey, I can visually see that you know that that is a smaller wavelength. So we love to see kind of drawings around our pictures and our information that I've given you. In science, there's multiple ways for us to explain things, and a lot of times jotting things down or interpreting a diagram in some way or a picture can help utilize that concept of being able to explain. Okay, now for these next set of 3 questions, it's going to have you circle one thing or the other in the choices. And these are all things on my electromagnetic spectrum. Eventually, you will have to do this without an electromagnetic spectrum. So it's helpful to remember the red Martians invade Venus using X-ray guns, right? Where I would remember radio waves, microwaves, infrared, visible, which is red through violet, ultraviolet, X-ray, gamma rays, right? And in terms of stuff over here being our low energy, low frequency, long wavelength, and over here going to be our high energy, high frequency, short wavelength. Okay, so let's do a few of them with this, and a few of them, if we can see, we can do it in our brains, using our brains. Okay. So it says, for each of the following pairs, circle the form of radiation with the longer wavelength. And guys, anytime I see any descriptive words talking about wavelength or frequency or energy, I immediately identify what that means with my arrows. So long wavelength means, okay, I'm dealing with a long wavelength. So my brain is thinking, okay, the long wavelength side of my electromagnetic spectrum was, it was that side over there with the radio waves, right? The really low energy. So my brain is already kind of in a good place here. So now I can look, I'm wanting to pick something that is on this side. I want to pick the one that is further towards this side of my spectrum. So the first choice is red light or blue light. Well, my red light is closer to the less energetic form of the spectrum than my blue light. So I'm going to say my red light has the longer wavelengths. And if it helps you guys to do that full chain of longer wavelength means lower frequency means lower energy, I mean, that sounds great to me, you guys. Like, the more that you can kind of put your brain in the place of what side of the spectrum that is, the better off it is for you to be able to answer questions that are like this. Okay, next up, which one is the longer wavelength, lower energy? Microwaves or radio waves? Well, both of those are kind of on the lower side of the spectrum. My radio waves are a little bit further with a little bit more of a long wavelength. Okay, let's see if we can do the next two in our brains. Infrared radiation or red light. Okay, so red light is in the visible spectrum, and it's like over here on the lower energy of the red spectrum. Just outside of that, though, is red light, our infrared light. So my infrared light is going to be the answer to that. Okay, next one. Once again, we're trying to pick the one that's over here on the low energy, long wavelength side of the spectrum. Gamma rays or UV radiation? Well, I know red Martians invade Venus using X-ray guns. Guns is gamma, so that is way over here. That means pretty much anything else that I would have you compare it to is gonna be towards that side, which in fact UV radiation is. And I can check my answers here on my electromagnetic spectrum and thank my brain for actually, using its skills to remember these things. Okay. Next one, it says, in each of the following pairs, circle the form of radiation with the greater frequency. Once again, I'm right, arrows, let's go. Greater frequency, greater frequency. Okay, all right. I know greater frequency means greater energy, and that means, it's going to be a short wavelength. So my brain is already like, we are on the part of the spectrum that is more frequently higher energy waves. So out of my two choices, I'm going to pick the one that's closer to that end of the spectrum. Okay, so my first one is yellow light or green light. Let's see. Yellow light or green light. Here's my yellow light, right? And here's my green light. It looks like green is going to be a higher energy wave. So therefore, my higher energy is also going to create the greater frequency. But once again, guys, mapping out all of these arrows, I don't have to confuse myself if my comfortability with frequency isn't really strong. But I feel real comfortable about describing a wave in terms of energy. So that helps me out a little bit more. So green light, we said, is the higher energy wave. Okay, next one, X-rays are gamma rays. Okay, gamma rays I already know is like way over there. So if that is not my answer, I will be super confused with everything I know. But we can check our electromagnetic spectrum and see if X-rays are a little bit lower energy than gamma or not. Let's check. Yep. Using X-ray guns. So my higher energy guy right there is going to be gamma rays. All right, let's see if we can do the next two with our brain. UV radiation or violet light. Okay. UV radiation is ultraviolet radiation, which is over here. And violet light is just past that, but now inside the visible spectrum, right? So UV radiation is going to be that higher energy wave, that higher frequency wave. All right, last one for this section. AM radio waves or FM radio waves? First of all, radio waves are way over here. Not very high energy, but if I were to compare my AM radio waves to my FM, I remember in our notes section I said the AM radio stations are for the old people and old people are much lower energy. So that must mean that my FM radio waves are a higher energy wavelength. Cool. Let's see if we're right. Yes, and we love that. Okay, see this next one together, which I absolutely love. Okay, it says, in each of the following pairs, circle the form of radiation with the lower energy. So lower energy looks like pow, low energy, right? Low energy also means low frequency. It also means a long wavelength. So you're already visualizing in your spectrum, oh my gosh, we're focusing on this end of the spectrum where things are like real sluggish and lazy looking, okay? So in that case, red light or blue light. Red is the lowest energy color in our visible spectrum. So I can go ahead and circle that right now, right? I could check my answer on my spectrum and be like, yep, there he is. Definitely lower energy than my blue in there. Microwaves or radio waves? We know radio waves, lowest energy that I have. And microwaves, have got to be a little bit more energetic. Not that much more energetic. Look, he only right there. But that means my radio waves, for sure, are the lowest energy waves. Next up, infrared. So infrared is just outside of red, right? Or red. Infrared, red. Infrared is going to be your lower energy. See how we're starting to kind of like piece this together and just use our brains by visualizing what these waves look like and using our red Martians invade Venus using X-ray guns. It is super helpful. Okay, then we got which one is lower energy? Gamma rays. Whoa, okay, gamma, we're way over here. And X-rays. Ooh, X-rays for sure, because gamma is the highest energy waves on our spectrum. And then finally, AM radio or FM radio waves. AM and FM are both there on the end, but the AM is for the old people, so they got the lowest energy, which I'm basically an old person now, so now that joke is not funny anymore. That is fine. So AM radio waves are the lowest energy waves, okay? I think you guys can tackle these next few ones pretty easily. I will do actually this first one just to kind of remind you what I mean when in terms of an indirect or a direct or an inverse relationship, okay? So it says, what type of relationship exists between frequency and energy? And guys, anytime I see these words, I'm like, ooh, frequency is V, energy is E. And for some reason, that helps me visualize the arrows a lot better. Well, we know frequency and energy, they both go up together or both go down together. Like that's what we mapped out up here and right here, right? So if I'm going up, and that one must be going up. In that case, it is a direct relationship. And what that would look like if we were to graph a graph of frequency and wave, or frequency and energy, we would see a direct relationship would show a line increasing up, which is a fancy way of showing that if one of those things gets bigger, the other one also gets bigger. It's that direct relationship. Okay. Fine, we'll just do the, oh my gosh, it's fine, we got this. Okay, what type of relationship exists between wavelength and frequency? I'm like, I gotta write those things. Wavelength, that's that guy, that upside down Y, that lambda, and then frequency. It's like, okay, from my spectrum, we know that if you got a really long wavelength, you got a low frequency. So long wavelength, low frequency, or short wavelength, high frequency. So we are going like this. That means we are dealing with an inverse relationship. So if one arrow is up or one value is high, the other value is low, okay? So this is an inverse relationship. The way an inverse graph would look is if I were to graph this versus this, you're gonna see a slope down. It is not a direct line down usually it is a slope down, but that is an inverse relationship. If you see the higher that the frequency gets as I move this way, the wavelength actually becomes lower. Amazing. Okay, and then finally, what type of relationship exists between wavelength and energy? Wavelength is this, energy is this. Helps to visualize your spectrum. We know the highest energy waves like this. Oh, and they got short wavelengths. Okay, so that's an inverse relationship too, right? So if I have really long wavelengths, that means they must be real low energy. So this is an inverse relationship. Okay, I actually love this next question, and it is unfortunately that we do not have printers that can print color things for you guys. But I did kind of document on this spectrum, this atomic emission spectrum, what colors some of the bands I would want you to be looking at to answer this question are. Okay. It says Mercury's atomic emission spectrum is shown below. Which color, either this yellow color or this orange color, corresponds to a larger quantity of energy emitted? Okay, so let's go back to when we were thinking about these electrons jumping through the energy levels. If I am asking you a larger quantity of energy, your brain is like, okay, a larger quantity of energy. We know based on the energy will give you a different size jump, right? If I want a large energy jump, that is going to be more energy for a larger jump. So we would say large energy, and I'm fine if you just want a capital E, that is fine to me too. Therefore, long jump, right? So that helps to kind of remember that too, right? So now I'm thinking that if I have a high energy, once again, my spectrum over here is not mapping me out in energy or frequency. It's mapping me out in, what, huh? Nanometers. Meters. Meters is a length. We measure light in wavelengths. Yo, this is wavelengths. Okay, so we're mapping myself out in wavelengths. Well, what's the relationship between energy and wavelength? Well, we just set up here that it's an inverse relationship, meaning high energy waves are going to have what kind of wavelengths? Short wavelengths, meaning the smaller numbers on my wavelength spectrum. And the tricky thing here is this wavelength spectrum is flippity-flopped. It goes from 400 nanometers to 700. And I know in our notes we wrote our visible spectrum 700 to 400, but that is just flip-flopping the rainbow. It is no matter. We would expect our violet waves with the shorter wavelengths to actually be over here. And then our red waves that we documented over here with these longer wavelengths are going to be over here. So it's just like a mirror image. It is not a big deal. We can still do hard things. Okay, so I'm going to pick the color that has the shorter wavelength. Out of these two colors, which one is towards the end of the spectrum that has the shorter wavelength? It is the yellow one. Yes? That is amazing. So I've answered the question and I've used my knowledge of this inverse relationship between energy and wavelength to figure out what color I am on this jump here. But keep in mind that these high energy colors are going to come from those long jumps, okay? And we're going to do some more problems dealing with the model of the absorption and emission of photons of light throughout the energy levels. Okay, let's go ahead and flip to the back. Here's where we get into the calculations, you guys. Okay, there are some differences between the honors handout and the on-level handout. I'm going to be working through the on-level handout, and I'm not going to do all of them. I'm going to maybe do the first, which ones am I going to do? I'm going to do the first 3 ones on the back, and there is a little tag at the end of question number 12 that is specific for honors, which I will go ahead and go through on that too. But once again, guys, here are my equations, right? C is equal to wavelength time frequency. Maybe we'll use this opportunity right now to remind ourselves that C is the speed of light is 3.00 times 10 to the 8th meters per second. Good idea to remind yourself what units I use for wavelength. It must be meters going into this equation. If it is nanometers, oh no, you must convert first to put it in meters and then you can pop it into the equation, okay? Honors classes, you guys will be doing that. On level, you do not have to worry. Okay. And then finally, frequency is hertz. I'm taking the time to write that because y'all about to have a lot of numbers down here and they are going to have these letters of the alphabet after them and you're going to need to know what that unit based on those letters is telling me of where it's supposed to go to find your equation to use. And then I have this equation, energy is equal to H times frequency. H is Planck's constant. That's another constant. So whenever you use H, you will always be plugging in 6.626 times 10 to the negative 34th. And the units for that are joules seconds. Yeah? And then frequency, his units are hertz. Energy, his units are joules. Okay? So if you see something with a joules, it is an energy. If you see something with a hertz, it is a frequency. If you see something with a meters, it is a wavelength. Now this one wasn't really represented in our notes, but this one is a kind of a combination of all of these things. Honors kids, if you want to be like, oh, how do all of these things come together to make this? You can actually use this equation to solve for energy if just knowing the wavelength. We can also use this equation first or this equation first and then plug it into this equation, which is what we did on the very last example problem in our notes. But you can do a one stop with that one. So honors kids, if you would like to, I think one of the last questions has you utilizing that. But you do not have to. I feel like that is one more equation for me to maybe have to memorize, and that sounds kind of terrible. But just be careful if you choose to split it up into two different equations. Make sure you do not incrementally round your frequency once you solve for that first in your calculator. Keep it in your calculator and hold on to it, and then type in what you need to type in with it to then solve for your final energy. Anyway, okay. And the units for all of these things are the same. Once again, these two are your constants, your Planck's constant, your speed of light constant. Once again, wavelength is in meters and energy is in joules, okay? Now, on level kids, we are working on making sure we can manipulate the variable we are trying to solve for. If you need the security of your triangles for these equations, your speed of light equation has the C on top, and then the wavelength and frequencies on the bottom. And then your energy equation has the E on top, and then your Planck's constant and frequency on the bottom, okay? I'm going to refer to the triangle so you guys can see how that shows what we're actually doing when we manipulate our equations. But we're going to see if we can kind of build up that skill a little bit better. Okay, here we go. What is the frequency of a radio wave with an energy of Okay, a lot of words. Okay, here's a number they've given me. Now, these are freaky stuff, so you guys, I do not feel, I've been doing this a long time, and I'm telling you, I do not feel comfortable solving these problems without labeling what that number represents, okay? It takes me 2 seconds to pop a little E above it. I know it is an E because it's got a J, right? And now I'm going to ask, well, what is it that they're trying to solve for? What is the frequency? What is the frequency? What is the symbol for frequency? It is a V. Okay, so I'm going to need to pick the equation that has E and V in it. It is that one right there. We love that. Okay, so I write that equation down because that is kind of like my foundation, my home base. But I'm asking you to solve for the frequency, this value right here. So if I'm going to solve for that, I want to isolate that variable first, where this equation will say V, our frequency, is equal to something else. Then that makes things not look so sloppy when I'm plugging in numbers and having to worry about moving all those numbers around. That sounds awful. Okay, so to get V by himself, what I got to do is, he's got this sneaky little thing stuck to him, an H. Got to get the H away by dividing by H, right? But if I divide that side by H, I got to divide the other side by H. Now this side that has an H on top, H on the bottom, they go away. So what I have here is frequency is equal to energy over H, yeah? And if you want, I would recommend rewriting that to your new equation. And we know in my class, I require you guys to show the equation. I'm fine if you show that, but I think it may be to our benefit to show it already manipulated to where what you are trying to solve for is like, bam, is equal to, you are ready to go. Because then that makes your brain have to do far few things. And you know that all the thinking you have to do for this next step is just popping in those numbers. That I absolutely recommend. So when you show your equation, you can do all of the workout. That sounds great to me, but I think that that would help us all a lot if we establish that equation in there in a way that it shows what variable we are solving for and what that is equal to. Okay, so I just talked a long time about that, so if y'all are like, move on. Here we go. So energy, and this is where the labeling helps. I'm like, that is the number that I get to use. So I will write 1.55 times 10 to the negative 24th joules. And yes, the units are important. I do not want to hear that. Okay, H. He's my constant. So I'm going to type in 6.626 times 10 to the negative 34th, and the units for him are joule seconds. Okay? So the result of this that I will solve for is going to be my frequency. So I said frequency was equal to that. I have my substitution of what it is equal to, and I will write my answer of what it is equal to. Keeping in mind, once I type this in the calculator, I'm going to have to round it. The only thing I round it to is how many sig figs are in that problem. 3 sig figs. We are ready to go. So I got my old calculator again. She's doing the most. Oh my gosh, my children were playing with that. That is fun. Okay, get out of there. Okay, I don't even know what that is. I don't think I've used whatever that was on my calculator screen since high school. Okay, here we go. E button, we are ready to go. So I go 1.55 E, right? And then my exponent is negative 24. And from that, I'm dividing 6.626 e negative 34. Yes? Amazing. We love that. Okay, so what we're actually doing here, did I type that in right? Let me see. Yes, okay. So what we're doing here is we are actually going to, that's a big old number, right? So we need 3 sig figs for this number. So the first sig fig we want is a 2. We want that 3. We want that next 3, and that's it. But we got to round that 3 up to a 4. So it looks like I have 2, 3, 4, but not just 2, 3, 4. That is 234. That is a giant number. I cannot round a giant number to make it way smaller than it's supposed to be. That means I just need to put some zeros here. And the zeros are not going to affect my sig figs as long as I do not put them a decimal at the end of the number. So it looks like I have 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. And the units, you're like, units. Well, that's why I write my units in here, you guys. So I see joules on top, joules on bottom. The only thing that's going to be left is this awkward a seconds on the bottom. But that's that hertz thing, that frequency, that 1 over a second. So this is hertz. And if you've forgotten, y'all, that's why I identified. This is what I was solving for. We know frequency is hertz, okay? You could totally also write this in scientific notation. I mean, that is a lot of zeros that I have had to write. If your calculator gives it to you in scientific notation, that is totally fine. To put it into scientific notation, I would move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be 2.34 times 10 to the 9th hertz. Both of those answers are totally acceptable, just making sure it's the 3 sig figs that the given number is given to you. So this is a great lesson on moving my things around from my original equation to get it into a format that makes sense for what I am to solve for. All right, the next one. I'm excited. This is getting fun. Oh my gosh, I'm such a nerd. Okay, calculate the wavelength of electromagnetic radiation whose frequency, blah, blah. Okay, I hate my number. Ooh, it's hertz. Ooh, we know that means frequency. Good, so my equation that I'm gonna pick's gotta have a V in there. What am I solving for? Wavelength. Which equation has wavelength and frequency? There she is right there. So I'm going to use her. I'm going to go C is equal to wavelength times frequency. Great. I'm not solving for C. I'm going to move some things around. I've got to get wavelength by himself. So in order to get him by himself, I got to get rid of his sneaky friend. And to get rid of his sneaky friend of frequency, you have to divide by frequency on both sides. So that cancels out frequency, which means my equation that is going to be more friendly for me to substitute into is going to be C over V. Now I'm ready to cruise. C is my constant, the speed of light. All of my wavelengths of light move at the same speed, which is crazy. 3.00 times 10 to the 8th meters per second, right? Units in there as well. And then I have my V, my frequency, which I've labeled over there, so I'm not confused about where am I supposed to get that value from. It is right here. So we have 7.5 times 10 to the 12th hertz. Amazing. Okay, so woo, here we go. So much fun. So I'm ready. I got scientific notation, so I'm using my E button, 3E, 8. It's real nice and satisfying. 3E, 8, that's it. We don't have to like do too many other things there. So that's the speed of light divided by 7.5 E and then 12. Cool. Okay, so my answer is 4E, negative 5. That's wonderful. So I'm a 4 times 10 to the negative 5th, right, is what that is meaning. But before I write this out, I'm going to, take a little glance at my sig figs. That's got 2 sig figs. So instead of just writing 4 times 10 to the negative 5th, 4.0, that works, right? Because it's got a decimal in that number. That is a trailing zero that I've told you just that zero is significant, times 10 to the negative 5th. And you're like, oh my gosh, what units? Y'all, we have solved for wavelength, length, meters, right? Meters. And once again, your units inside of the substitution can help you. Hertz is over a per second, so that would mean those seconds cancel out to where you would be left with meters at the end. Good. So now we're picking up some steam. Let's keep going. I cannot tell you how much this circling totally helps here. Okay, determine the energy of a photon. Oh, look, I mean, I'm just jumped into the circling, and I will read the words later, but I'm like, this, I gotta have at least this. Hertz, another frequency. Now they're asking me to determine the energy. Energy, E. I need an equation that's got frequency and energy, so I'm using this guy right here. So E, I'm writing it down first, and then I'll see if I have to manipulate it based on what they're asking me to solve for. Well, they're asking me to solve for energy. I got that. Yay, he's already isolated. So I can plug straight into that and keep cranking through. Okay, so energy is totally going to be equal to Planck's constant times that frequency that I have right there. Okay, so Planck's constant is 6.626 times 10 to the negative 34 joules seconds. And then we got my frequency of 3.55 times 10 to the 17th hertz. Yes? Lots of scientific notation stuff happening here. What is happening? Okay, cool. We got this. Okay. 6.626 E negative 34 times 3.55 E, what is it, 17. Okay. Yes. Okay. Once again, looking at that only number they gave you in the problem, the one that you circle, he determines sig figs. Once again, the constants, my Planck's constant of H and my speed of light constant of C, they are infinitely significant. They are not important in terms of the measured values. This is a measured value telling me how to round my sig figs. So I got 2.35, right? And my 2.35, it is not just 2.35, it is times 10 to the negative 16th, times 10 to the negative 16th. And I have solved for an energy. Energy is always joules. Your units help you out here. His is joule seconds. This is over a second. Seconds go away. I just have joules at the end, right? Looking at this is amazing. Okay. So on our on-level kids, I think we're probably feeling a little bit better about manipulating our variable and plugging in and making sure we're getting that right answer. And I'm super excited and so proud of you. Honors kids, I kind of want to bump up here. I'm pretty sure your problem number 11 had you, in fact, I have y'all's here. Your problem number 11, yes, asked for you to solve that wavelength in nanometers. So once again, I'm going to rewrite my 4.0 times 10 to the, what was it, negative 5th? So we solve for that. So if they ask for you in nanometers, you're just gonna have to take an extra step and convert that to nanometers, which is gonna be a little bit smaller, right? So to take it a little bit smaller, we know that we are going to move that decimal 9 places in that direction, right? So if I'm going to move that decimal 9 places in that direction, if you want, sometimes I find it a little bit helpful to take it out of the scientific notation just so I can kind of see that decimal. And that is an option for you. So you have 0.00040. So that was what that would be without the scientific notation. And now I can see that. And if I move it 9 places that way, 1, 2, 3, 4, 5, 6, 7, 8, 9. So then I have, that would be 4 with 1, 2, 3, 4 zeros. 1, 2, 3, 4 zeros. Nanometers. Okay. Another thing that you can do, as we talked about this last time, I find that to be a little bit tedious. I like to look at this times 10 to the negative 5th, and I'm like, I'm incorporating 10 to the 9th because it's 9 places away. So what you can look at that is when you're multiplying this stuff, right? You can add these two things together. So I would add a negative 5 plus 9, and that's going to give you your new exponent of 4. So this I could then directly turn into nanometers by saying, hey, okay, I'm just going to add 9 to that. And you would just immediately get 4.0 times 10 to now the 4th. Nanometers. It is whatever way you feel comfortable. Honestly, I've gone through phases of my life where I was like doing all that, and now I feel like this year I am in a phase of my life where I'm like, I just want to add 9. But keep in mind, if you are given nanometers and you need to use that wavelength to plug into one of our equations, you have to go the other way. You've got to convert it to meters first. And I think there is a problem down here. Maybe there's a problem down here. Ah, yes. nanometers, right? To where you would be then adding that 9. So here, we can practice this. Look how smart we can be. Okay, so this is technically 5.06 times 10 to the second, right? So instead of adding 9, we're going to subtract 9 from that to get it 2 meters, right? So 2 minus 9 would be a -7. So I could say, therefore, that would be 5.06 times 10 to the -7th meters. And then that is the wavelength that you will be using for that problem to plug. Oh, I even told you, I made this suggestion. Look how nice I am, okay? And then that's the wavelength that you will be using, right? To then, apparently, it looks like, solve for the frequency. Yes. Okay. So honors kids, y'all gonna be dealing with the wavelength of meters to nanometers conversion. That is okay. It's just moving 9 places. So hopefully this gets you a little bit more comfy and cozy with this concept of these speed of light calculations and the energy of these photon calculations. I find this stuff to be really fun. It's not super tricky, but we are dealing with the scientific notation-y numbers of it all. So I can understand why it could be a little bit more tedious in terms of requiring more of our time to make sure we can really lock it down.